lecture, basically the first 5 classes, just to recap, I know we've had reading week, but let's recap where we are. So the first 5 classes, we really covered some of the fundamental principles of reinforcement learning. So we looked at dynamic programming, we looked at Bellman equations, we understood the structure of Bellman equations, we developed model-based and model-free algorithms for solving MDPs. And really, we started to look at different ways we can move between these things by looking at things like eligibility traces, TD lambda, this spectrum between Monte Carlo and bootstrapping methods. And in a sense, those first 5 lectures represented the core of what we're going to teach on this course. So for the second half of the course, what we're going to do, we're going to look at methods that will scale up. So you've probably been wondering, in fact, I've had people come up to me at the end of classes and say, well, these methods are interesting, but what happens if you have a really big MDP? What do you do? Do these methods scale up? What do you want to do if you actually want to solve a large and interesting problem? And so that's where we're going to start today. We're going to talk about value function approximation. So what we'll do is we'll have a brief introduction, and then we'll basically break this up into 2 parts. First of all, incremental methods, which will give you an idea of how to sort of extend the methods that we looked at, Monte Carlo methods, TD learning methods, how we can extend those methods to basically step-by-step methods that do something a little bit like stochastic gradient descent, in that they see one item of experience, and they make one update. They update the value function a little bit based on one new piece of experience. And then the final part of the class today, we'll look at batch methods. And these batch methods will in one step jump to the most efficient solution to all the data that the agent has seen so far. That's the idea. So we're going to start with incremental methods, we're going to move on to batch methods. Both of these are very widely used. So all of the methods that you'll hear about today are among the methods which are most used in reinforcement learning and practice. Okay. So in general, if we want to solve large problems, what do we mean by large? Well, some of the methods, some of the problems that have been solved by reinforcement learning include things like backgammon, which was famously solved by solved, I mean, came up with a very, very strong player. And this is a game which had 10 to the 20 states, and people were able to use value-based reinforcement learning methods to solve this problem and come up with a very, very strong player that could beat any human. And myself and other researchers have worked on the game of Go. This is a problem with 10 to the 170 states. And if you want to work on continuous state spaces, such as we had the example of the helicopter in the previous lecture, or robotics applications, there you have continuous state spaces, possibly continuous action spaces. So in a sense, you have an uncountably infinite number of states and actions. So the big question we're sort of left with then is, how can we scale up the model-free methods that we looked at, both for prediction and for control, that we looked at in the last 2 lectures? How can we scale them up to these sort of larger problems? And we're going to use one sort of general principle to solve all of these, which is value function approximation. So in the lectures so far, what we did was we basically represented the value function by a lookup table. So what we mean by that, we basically mean that every single state has its own entry in this table. For every state, we estimate the value of that state separately. So if you have 1 million states in your representation, in your state space, well then you need 1 million entries to this lookup table. And you have to estimate the values of each of those separately. Or we looked at control methods that were based on the action value function Q. So remember, we had the state value function V and the action value function Q. And in the state value function, now you need an entry in your lookup table for every state action pair. So now you've got the cross product of the state space and the action space. So a very, very large number of states and actions in a real large problem. So there's 2 real problems with this. The first is the obvious one, that there are just too many states and actions to store these things in memory. So you've got a lot of states and a lot of actions. Well, this table is just too big to even store on your computer if you've got 10 to the 170 states or a continuous state space. But there's a second problem, which is that actually the learning problem, that even if you could store it in memory, if you've got millions of these things and you're learning about each one separately, it's going to be very, very slow to learn. And another way to put that is that there's no generalization. So you really want to be able to generalize from the value of one state to the value of a similar state. You want to be able to observe that if your robot's in one configuration and its arms are like this, well that's probably quite similar to a similar configuration where its arms are just moved a little bit. You don't want to learn about these things separately. So our solution, which we're going to look at in this particular class, in this lecture today, is to estimate the value function using a function approximator. So the basic idea is we're going to have some function approximator. Here we've got a parameter vector theta. We're going to represent some function representing the function approximator. This could be a linear function approximator, it could be a neural network, it could be any number of things representing the value of all possible states that you might be in. So this thing is now some function approximator. We've got some parametric, maybe it's a spline that we're trying to fit this thing to represent the value function as well as we can, given the parameters that we have in our function approximator. So if we're going to make this approximation, we're going to give up on the idea of exactly representing the true value of every state in the state space. Instead, we're going to approximate the value of all these different parts of the state space by some function that sort of maybe smoothly fits amongst all these different values. And similarly, we're going to try the same idea when we move to control later on. We're going to try and also similarly represent the value of all different states and actions in our joint state and action space. So here we're going to have some function approximator that represents the value of all different state action pairs that you write in. So essentially this thing is trying to estimate for all different points, for all different states S and for all different actions A, how good is it to be in that state? And this thing basically estimates it using some fitted approximation to that value function. This thing might be some very big, spiky, might be have discontinuities, it might be a very complicated object, and typically here we might have something much smoother that we're estimating with some more small number of parameters. There are non-parametric variants of these, but we're not going to talk about those in this lecture. Okay. And the goal, why are we doing this? Can everyone see down to this bottom line, by the way? Okay, good. The general idea, one of the core ideas that we gain from having this function approximator is this ability to generalize from seen states to unseen states. So it might be that you've just seen a return from one particular state, and because we've got some function approximator, we can use that to very quickly fit our curve to that particular point that we've seen. We might have seen a return of plus 100 from one particular state and action we chose, and now we can generalize to similar states that we haven't seen yet, and use that estimate to very quickly figure out what to do in other related states and actions. And what we're going to do, okay, I asked too soon, can everyone see that line? Okay, good. Is we're going to update the parameter, our parameter vector theta, using, in the first case, Monte Carlo learning, and in the second case, bootstrapping methods based on TD learning. So basically going to go through the same kind of technology that we saw for our prediction class, we're going to reapply that, but using function approximators, where we no longer have one value for each distinct state in the state space. Is that clear? Okay. So, you've probably seen in your supervised learning class and in the rest of machine learning that there are many, many different ways that you can approximate a function. So some well-known function approximators include artificial neural networks, decision trees, nearest neighbor approximations, Fourier or wavelet bases for representing functions, or what we call coarse coding, which is basically where you just have a bunch of features thrown down to cover different parts of the state space in sort of lumps, if you like. We'll look at that in more detail later. And in principle, any of these could be used. So which one should we choose? Well, it's not quite the same as just supervised learning. So what can we say about this? Well, we might be able to say at least some things which are special about reinforcement learning, which might guide our choice a little bit beyond what you might do if you were just doing supervised learning. And some of those properties of reinforcement learning include the nature of experience. So we don't, unlike supervised learning, we don't have IID data. So the return that you get at one time step is very, very correlated to the return that you'll get at the next time step. So if you just happen to have wandered your agent into a very rich part of the state space, whereas there happens to be a big pile of gold around, you're probably going to find that you get a lot of gold at the next time step, as well as the previous time step. So in addition, the methods we looked at for doing control were based on this idea of policy iteration, where we moved through a whole sequence of different policies, improved the policy, improved it again, improved it again. As a result, each time we evaluate the policy, we find that evaluation process is non-stationary. We're trying to evaluate a policy which is changing. We're continually improving our policy as we gain more experience. And if we try to evaluate that policy, we find we have a non-stationary set of data. So typically we want to search for function approximators that help us do non-stationary function approximation. And finally, and importantly, what the agent does actually affects the world it's in. So this again is very different from supervised learning. The agent gets to control where it goes. So it can actually choose to explore, if it doesn't know much about some part of the curve, it can say, oh hang on, I want to go and explore that part of this curve and figure out my function approximator a bit better. So the agent is actually able to explore, and this is sort of part of the problem. So, you know, what can we really say then? Which function approximator should we use? Well, maybe the only concrete thing we could say is that what you'll find is that in general people tend to fall back to simpler function approximators in RL than you might find in supervised learning, because we're in a slightly more complicated setting for these three reasons. So people tend to look at simpler methods that support non-stationary methods. And so in the first part, where we look at the incremental function approximation, we'll look at some very straightforward approaches based on linear function approximation, which is very popular in RL. And feedback is also delayed. Okay, so incremental methods. So we're going to start with a principle that's hopefully familiar to most of you, which is gradient descent. So I'll just remind you of how this works very briefly. So the idea is we've got some parameter vector theta, and we've got some objective function, this is j theta, which is just going to define some surface that we're trying to optimize. So we're talking in a very general sense here. There's just some function, we want to optimize that function, we've got some parameters we can tweak. How do we find the best or some good parameters? And so all we do is we follow the gradient. So here we're just looking at the partial derivatives, we're looking at the direction in each of the different dimensions. So this is for each of the different dimensions of the parameter vector. We look at the gradient in that direction. We form a vector of all of those gradient components. And this is the gradient of the objective function. And if we want to find a local minimum of our objective function, then all we need to do is follow that gradient. So we take a little step. So this alpha is going to be the step size throughout this class. So we take a little step, so this is a downhill step, that's the minus, we want to move down the gradient in the direction of a little bit, in the direction of this gradient. And that's just going to continually take us downhill and downhill and downhill, and when we stop moving downhill, we must have found the local optimum of this function space, this objective function j. Okay, so what we're going to do is use stochastic gradient descent to approximate our value function. So now we're going to sort of instantiate that basic gradient descent framework for value functions. And so here what we're going to do is say, okay, well, the objective which we're going to care about, let's say, is the mean squared error. You can consider other objectives. We'll consider this sort of L2 loss throughout this class. So this is the mean squared error. So this is the expectation if you're following your particular policy. We want to do policy evaluation here. And so if we want to do policy evaluation, what do we want to know? Well, we basically want to know how accurate is our estimate of the value function. So we've got some estimate of the value function, which is our v theta. We've made this sort of surface, our curve, that we're trying to use to estimate the value function. We want to know, well, what's the difference, the squared error between our estimate and the true value function at that state s. And we take the expectation over all the states that we're actually going to visit by following this policy. So the expectation says, okay, well, we're going to follow some particular path through the state space. We want to know, on average, what's the error going to be, the squared error between our actual true value function and our estimate of the value function. So that's the objective which we're going to try and optimize, the mean squared error between the true value function and our function approximator. Now this, we now can just substitute in our gradient descent algorithm. So what does it look like here? Well, we're going to substitute in our same gradient descent idea. We're going to update the parameters a little bit downhill in the direction of this gradient. And the gradient, we can just apply the chain rule, and we see that we end up with a gradient of this form. So basically, we're going to take the gradient of this objective. The gradient can be pushed inside the expectation. And what we end up with is this error term here multiplied by the gradient of our function approximator. That's just the chain rule. Okay? So what this actually looks like now is we're basically saying, if we can just sample this expectation, what we're going to do is just sample this expectation, and what we find is that we're going to update the parameters a little bit in the direction of the error that we've made. So this is the error between our estimate of what the value function was and what the true value function is. So we're going to push the parameters a little bit in the direction of that error, multiplied by the gradient of our function approximator. So you can think of this as sort of a term telling you how big the error is that you've made, and this is a term telling you how to adjust your parameters in the direction of that error. So should I move my parameters this way or that way in order to change the error? So this is how big the error is, and this is how to update the value function. So this should look very familiar from some of the other classes we've had. We've got a step size multiplied by an error term multiplied by something which is going to be a bit like a feature here. I'll step through this in a little more detail in a second. Okay, and the expected update of this particular thing, so if we look at this, so stochastic gradient descent, the whole point is that in expectation, on average, if we just keep doing these updates, keep doing these updates, keep doing these updates again, we will end up with the true gradient direction. That's the whole idea of stochastic gradient descent. We just sample this for each state that we arrive in. We're going to look at that particular state and we're going to update a little bit based on what happened in that state. We're going to look at the error we saw in that state. And on aggregate, by just walking through the state space repeatedly, in expectation we're going to recover the true gradient. For most of this class, a much more concrete representation of the value function to make this more, just more specific to understand what's going on. So what we're going to do is we're going to represent the state by a feature vector. So we're going to say, okay, how can we summarize the state S? We basically want to represent our value function in terms of some key properties of that state. Like maybe it's the robot's location, maybe it's the XY coordinates of the robot, maybe it's some other properties of the state that we care about. And what we're going to do is call that a feature vector. We're going to pick out all of these different functions. So some examples might be, maybe you've got a robot moving around, and we're going to represent the state of this robot by its distance from a bunch of different landmarks in its region. And those would be, this might be, how far is it from the first landmark? How far is it from the second landmark? All the way down to the nth landmark. And now we're going to summarize, instead of looking at the exact state of that robot, we're going to throw that away. We're going to replace it by this sort of representation, this feature vector representation of what's happening to the robot. Similarly, we could, if you were trying to predict the stock market, you could look at trends in the stock market. You could look at sort of the derivative of the stock market, or the second order derivative, or the third order, how quickly things are changing over different periods of time. These might be your features, or you might have indicators of the stock market. These might be your features if you're trying to predict something about the stock market. Or if you're playing a game, like the game of chess, you might consider, well, where's the queen? Or do I have a knight in the middle of the board? Or do I have two connected pawns, or do I have a passed pawn? These kind of configurations in the game might make useful features. And now when you want to understand the value of your position, you don't need to look at the complete configuration of all pieces anymore. You just need to say something like, oh, well, I've got a queen and a rook, and my opponent's got 2 pawns, but one of them's a passed pawn. So I'm winning by +7 to -2. Okay. So what we're going to do is use these features to build up an estimate of the value of being in any one of these states. And the way we're going to do that is sort of the simplest way you might combine these things together, which is linearly. In other words, what we're going to do is we're going to take our feature vector, we're going to take the dot product of that feature vector with some parameters theta. So this is basically just writing it out. This is exactly that dot product. We're basically summing over all of the features, and we're going to give each one of those features its own parameter value. How good is it to have this particular feature? So if you imagine that these are binary features, like whether you have a queen in the game of chess, this feature might be, do I have a queen? And this parameter would be, how much is it worth to have a queen? Or in the robot example, this might be, how far am I from a particular landmark? And this parameter might be, how good is it to be a certain distance from that landmark? And we're assuming that these things scale linearly. And we're just going to sum over this linear combination of all of the features. And that's going to be our estimate of the value function. So one nice property which is worth noticing is that if we go back to our objective function, the mean squared error, we now plug that in. So now here we're looking at the difference between the true value function and our value function approximation here. So the mean squared error between the true value function and our dot product thing which we formed out of these parameters and features. But we've got a quadratic objective function. So it's quadratic in theta. So theta, these are the things which we're trying to optimize. And the objective function, this j, is quadratic in theta. So what does that mean? Well, it has the nice property that because it's quadratic, we basically just have a bowl. And so if we use our gradient descent algorithm, or stochastic gradient descent, it means that we're going to find a global optimum. There are no local optima when we do this. If we just keep going down, we will get to the optimal solution. We'll find the best fit for our parameters theta. We'll find the best value of our landmark features and how much each of those is worth. And the update rule that we use for stochastic gradient descent is kind of particularly simple in this case, where this gradient which we've been looking at, so the gradient of this function approximator, the gradient of this dot product here with respect to the parameters theta, is just the feature vector. So this gradient, this thing where we were looking at this thing here, now we're literally just going to plug in this, so for the gradient of this dot product is just the feature vector, it's just this thing here. Okay. And so the update rule becomes very simple as a result. So the update rule, which I hope you can see, is that we change the parameters a little bit in the direction of the error between what we thought the value was going to be of this state and what the true value of this state was. So you update a little bit in the direction of this error, multiplied by your feature vector. So you can think of this as like a way of solving the credit assignment problem. It's like saying, well, I saw some error. Now, which of the parameters was responsible for that error? And when you have a linear function approximator, the solution is that you basically say the error is credited in proportion to how much those features were on. So if you were in a situation where you're really, really close to one of the landmarks and that resulted in a big error, well then you would credit that particular feature more than the landmarks that you're a long way away from. Or if you're in a chess position where you have a queen and you have a knight on an outpost, and as a result of that you end up with a big error, well those are the features which you'll update more, not the ones which were off in that position. You'll update the features which are actually present there. And so this update you can basically think of as step size times prediction error times feature value. Okay. So there's a problem so far, which is we've sort of assumed the existence of this oracle here. We've assumed that someone's telling us the true value. And so what we're going to move on to now is how to deal with that. We'll do that in just a minute. So first, one thing to say, which is that in the first part of the course where we did table lookup, really this was actually just a special case of linear value function approximation. So we can define some special features, so let's call these table lookup features. So this thing basically means an indicator function. So if we set up our feature vector to have the following form, where we have an indicator function saying, am I in state 1? Am I in state 2? Am I in state 3? All the way down to, am I in state n? Then this feature vector basically recovers exactly the table lookup representation that we used in the first part of the course. And if we go back to our... and so what do the parameters mean then? Well, the parameters now mean the value of each individual state. So we're going to take this dot product of our features with the parameters, and so now what's going to happen is we can only be in one of these. And so we're actually saying that the value of being in any state is given by the dot product of these indicators with the value of how valuable it is to be in any one of those states. So these parameters literally correspond to the value function for each of these individual states. So we can recover, so it's just a sort of side point to note that everything we've seen so far is a special case of this framework. People should stop me if this isn't clear. Okay, so let's move through some examples. So here's an example of coarse coding. So this is one example of how you can use a linear function approximator. So let's imagine you've got some two-dimensional state space. So this could again be, you've got some robot moving through a two-dimensional space. The actual state is, say, just its position in 2 dimensions. But what we can do is just sort of divide that up into different regions. And so we could throw down, say, some circles, and our features could be things like, is the robot in that circle? And the nice thing about this is, as opposed to discretization, which sort of has this mutually exclusive partitioning of the state space, what happens when you use coarse coding is many of these can respond for any particular position. So let's say the robot's actually here. Well, then you would say, well, okay, this feature has value 1, it's in this feature. The robot's also in this circle, so that feature would have value 1. It's also in this circle, so that feature would have value 1. And all of the other circles would have value of 0. So you'd end up with a very sparse binary feature vector, large sparse binary feature vector. And it turns out these are very efficient to work with and can quite nicely capture many of the different sort of aspects of the variations across the state space. If you want more resolution, you throw down more of these things into your state space. If you want more generalization, you throw down bigger circles. So let's try and make that a bit more concrete. And the parameters now are just going to be the value of each of these features. So we're going to basically take our state, original representation, the x and y coordinates, we're going to expand that into this sparse binary feature vector. And we're going to take a linear combination of those sparse binary features with multiplying them by this parameter vector, and that's going to give us our function approximator. So basically just adding together the values of the circles that we're in, and saying, well, if I'm in this one, and this one, and this one, then the total value we're going to use to estimate the value is the parameter corresponding to this one, plus the parameter corresponding to this one, plus the parameter corresponding to this one. So it's a very simple way to approximate value in terms of just simple features, binary features. Okay. So we can choose the shape of these things, we can choose the size of these things. So we could decide to put down small circles, and if we throw down lots of small circles, we get quite a lot of good resolution in our state space. But what we have is a sort of narrow generalization in that if the robot's over here, well, we assume that there's some sharing. This parameter here, this feature here, helps us share from the robot being here to the robot being anywhere within this circle. So you get some generalization within this region because this parameter will be shared, the value of this parameter is shared amongst all of those different locations. Equally, we could choose to have a broader generalization. We could have much bigger circles, and now if the robot's here, we're going to generalize amongst all of this state space. You could choose to do it asymmetrically as well if you wanted, have more generalization in one dimension than another. These are all just examples to get you thinking about how you can use sort of straightforward function approximation architectures that scale up very effectively. So here's an example of how this might work with coarse coding. So here what we have is basically 3 different examples corresponding to narrow features. These are sort of very, so now we're just doing this in one dimension. We've got a one-dimensional function, which is basically a step function that we're trying to approximate. I'm going to try and approximate that by stochastic gradient descent. This is just supervised learning for now, just to get the flavor of it. We're going to try and learn this value function, essentially, from using either very thin features, so these features are kind of very thin regions that we're going over. So these aren't circles now, they're just like step functions that we're responding to. And here we've got medium-sized features, and here we've got very broad generalization. And what's happening is we're going to randomly pick different points, so starting from 10 different examples all the way down to 10,000 examples. And what we're going to do is run our stochastic gradient descent update based on examples of the desired function. And what you see here is that when you have this very fine generalization going on, what you end up with is something which learns quite slowly, but ultimately ends up with a quite high resolution estimate of this desired function, which might include some sort of slight oscillations there. If you use broader features, you can learn much more quickly. The reason you learn more quickly is that just from a few examples, you're able to generalize to a much broader range quite quickly. If you use broader features still, again, after just 10 examples now, you've got quite a smooth estimate of this function. And so ultimately, you're able the generalization determines how quickly you learn, and the resolution, how many of these things you have down, determines the ultimate quality of your function. So these coarse coding function approximators help you independently trade off resolution and generalization. Okay. Right. So far we've just been doing essentially supervised learning of a value function. We've assumed that someone's been telling us v pi. But we're really doing reinforcement learning here, so there's no supervisor, we just have experience, and at the end of that experience we see a bunch of rewards, and by trial and error the agent has to figure out how to do better. So what do? Well, in practice what we do is we substitute. We take our v pi of s, this is the true value function which we were so far imagining that the supervisor gave. What we're going to do is substitute a target for that v pi of s. And the question is, what should that target be? Well, if we're doing Monte Carlo learning, the target is the return. The return is an unbiased sample of v pi. So we're going to substitute in our vt. This is the sum of all the rewards, all the way through the trajectory from time step t onwards. So we're going to use that as the target which we're going to move towards. So here we see, again, we're going to update the parameters a little bit in the direction. This is the step size multiplied by the error between our return, how much reward we actually got, minus how much reward we estimated we would get. So our function approximator, multiplied by this gradient term here. And for TD0, if we were actually doing TD, well, the target, instead of being the whole return, we would just look one step ahead. So instead of looking at the returns cumulatively all the way towards the end of the episode, we'll do this one-step bootstrapping. So the target will be the TD target, the reward, plus the value function of the next step, discounted by gamma. So we're going to, again, look at the difference between, we're going to update the parameters a little bit in the direction of the difference between what we thought, how much reward we thought we would get, plus our revised estimate of how much reward we thought we would get after taking one step. So that's our error. So we're going to take a gradient step direction based on that error multiplied by something which assigns credit to the different features. This is, in the linear case, just our feature vector phi. And for TD lambda, you remember this spectrum that sort of interpolates between Monte Carlo and TD0, then we plug in the lambda return. So the lambda return was this average, exponentially weighted average of all the different instep returns. We plug that in. So we look at the error between our estimated return and our lambda return. And that's what we use as our error term there. So what we're doing now is we're basically we've moved outside of supervised learning. Moved outside of supervised learning, we're plugging in different estimates of the true value function. These are sample estimates. So how do these work? Well, if we do Monte Carlo learning, this has a nice property. The return is unbiased. It's just a noisy sample of the true value. So in expectation, this really is the true value function. So if we looked at the expected value of Vt, well, that is the definition of V pi, remember. So what this means is we can kind of think of this as just straight supervised learning. So it's straight supervised learning in the sense that for each of these states that we start in, you can imagine we start in state 1 and you see return V1. If you started in state S2, you ended up seeing return V2. And you just sort of treat these, even though they're not actually IID, you treat it just as if it's an IID data set. And you can treat this as a supervised learning problem, where from each state you got some return, and now we basically want to fit this training data to our parameters to find the best fitting value function from that data. We're going to do regression, basically. So this algorithm is called linear Monte Carlo policy evaluation, and it's just linear regression applied to the returns. So it's linear regression where we're trying to regress our features to the returns. We're basically going to try and figure out how much we should weight each of those features so as to best predict the returns. So it's linear regression. So all we're doing here is we're updating by stochastic gradient descent the parameters a little bit in the direction of this error multiplied by the feature vector there. So you might guess that because this is unbiased and it's a noisy sample, and because we're just doing linear regression, that this has to work. This is pure gradient descent. So Monte Carlo evaluation, this linear Monte Carlo policy evaluation, really does converge to a local optimum for a general function approximator and a global optimum for our linear case. Okay. Now what happens if we use TD learning instead? So we can plug in the TD target, this our revised estimate based on one step of how much reward we're going to get. So this is a biased sample of the true value. It's no longer an unbiased sample, in that if we take an expectation of this, it's no longer the true value function, and that's because we've got this function approximator here. So it's not really able to express the true value, even if we've got our thetas as well as we can. There's going to be some bias introduced by a function approximator. So the TD target is a biased sample of the true value. So what happens if we plug that into our gradient descent-like idea? Well, we can still think of this as something a little bit like supervised learning. So we can imagine that from each state, we basically end up with a target, and the target is basically just our TD target. So if you're in state S1, you end up getting a one-step reward of R2, and then ending up in state S2 with a value of S2 according to your function approximator. So we're basically saying we're going to treat this as a training pair. That I was in state 1, and I ended up with a target, a revised estimated value of R2 plus the reward after that step. And similarly, if you started in state S2, you would predict that the amount of reward you'll get from there is one step of reward plus the remaining value. All the way through. Yeah, all the way through to the end. And so we can think of this as a little bit like supervised learning. And if we just plug this in and sort of substitute into our supervised learning update, yeah, question?
But each time sensitize it, the old one from the previous step when you in the TD.
So which theta to use? Is the question whether you update theta between?
I mean, when you update theta, you have to the target is like reward plus gamma, the value of next state under the previous value of theta. So
yeah.
Okay.
If you're doing it online, which is what people do in practice, then yes, you update the parameters and then you reapply it. So you think of this at each step, and this is also true in, yeah. So hold that thought. So yes. So what's happening is that the theta is changing as we develop this, and that does mean that it's slightly more complicated than the supervised learning case. So the bias is itself changing. We've introduced some bias into the one-step estimate of the value function, and that bias is sort of changing and evolving as we modify our value function. And so there is some bias, and we hope that bias gets reduced. But the question is, does this lead to anything reasonable? So you've got just the right intuition that this isn't necessarily sound. And so the question is, does it work? And so what we're really saying is we've done something a little bit naive here, which is we've just substituted in. We sort of just changed our target. We said, okay, when we were doing supervised learning, we could just plug in the return. And what we're doing now is we're substituting something in. We're substituting in our one-step TD target, and we're claiming this is a valid algorithm. But exactly as you say, there's some bias involved in this target. So have we really? Does this really lead to a legitimate algorithm? So let's just look at the algorithm first and understand what it's doing. So what we're doing is we're updating the parameters again a little bit in the direction of this TD error, the difference between what we thought we were going to get and our revised estimate of what we were going to get after taking one state, multiplied by our feature vector. And the good news is that despite the fact that we've just done this by substitution, that if we're using a linear function approximator, then this still converges somewhere close to the best you might hope for. So it converges within some reasonably tight bounds of the global optimum. And there's a sense in which it is finding the optimum in terms of the Bellman equation and theta. So with linear function approximation, this is a sound algorithm. So we can also do this with TD lambda. I won't dwell on this too much. Except to say that when we use the lambda return, we also end up with a biased sample. So unless lambda is actually 1, in which case we recover Monte Carlo, then the lambda return is again a biased estimate of the value function. And it's biased because our lambda returns include all these n-step returns, and each of the n-step returns uses a v theta at some number of steps downstream. So each of those n-step returns is based on plugging in bootstrapping from the value function after some number of steps. And so we have a biased sample. But again, we can do the same thing. We can just view this as supervised learning. We can plug in our lambda return as our target. We can replace the return with the lambda return and treat this as supervised learning. And if we do that, we basically end up with something called, this is the forward view version of TD lambda. So if you remember in the TD lambda class, we had a forward view and a backward view. So the forward view, basically we just plug in our lambda return, and we end up again with a step size multiplied by an error term multiplied by our feature vector. But there's also this backward view. And the backward view for linear TD lambda, I'm just going to tell you without proof, so statement without proof that the forward view and the backward view are again equivalent, just as we had in the table lookup case. They're again equivalent if you were to update offline, if you were to accumulate all your updates throughout the course of your episode, and then do those updates once at the end of your episode, then the forward view and the backward view are the equivalent. And so this gives you this sort of mechanistic viewpoint where we can, without looking forward in time, we can at each step just do a very simple update and do a TD lambda update. And we can do that again with linear function approximation. And it looks just like the TD lambda algorithm, except for one small thing. So we've got our TD error, which is our standard thing, the difference between what we predicted. So these should be E thetas. But it's the difference between what we thought we were going to get and our revised estimate. That's our TD error. We've got an eligibility trace, which we're just going to discount by lambda at every step. But now we're going to update our eligibility trace, instead of updating it just by this indicator function that we had before, saying, am I in this state or not? Now we're going to update it by the feature vector. So we can think of this as credit assignment over both space and time. The credit assignment over space is basically saying, well, which of these feature vectors are responsible for the error? And the credit assignment over time is the fact that we now accumulate these step after step after step. So if one particular feature happens a lot, and one of those features is on for many, many successive steps, and then we see a big error, well then we'll assume that that is the feature which is most responsible for the error that we saw. And that's so we'll update that parameter more than the other parameters to correct the error that we've seen in our prediction. So I know I'm rattling through quite a lot of variance here, but I think the reason that we can go somewhat quickly is that we're essentially reproducing the same spectrum of algorithms that we had when we were doing prediction, but with this change where we've basically replaced this indicator function that we had for the table lookup, we've replaced with a feature vector now. So everything is now multiplied by a feature vector. We're updating all of the different parameters in proportion to the feature vector, in proportion to the features. Okay, any questions before I move on to control? So this is, so far we've dealt with prediction, so we've been doing basically policy evaluation with approximate value functions. And we've been looking at incremental methods based on stochastic gradient descent for updating and estimating the value function, using linear function approximation in particular. Okay, so let's move on to control. Right, so we had this basic sort of framework for control that we had before, where we've sort of alternated between policy evaluation and policy improvement. And we're going to use the same framework here, but with one change, which is now we're not able to exactly evaluate our policy as we were before. We're now going to use something like approximate policy evaluation. All we can hope to do, is to find the best fit to our parameters that we can. So we've got some parameters theta. We're going to make sort of, in each step of this iteration, each time we evaluate the policy, we're just going to try and fit our parameters as best we can to Q pi. So each iteration, what we'll do is we'll alternate between fitting our parameters to our the current policy. So we're going to try and figure out the value of the current policy. And then we're going to improve the policy. We're going to do that using epsilon greedy policy improvement, just as we did in the control class. So what does that look like? Well, it's kind of this picture sort of is supposed to illustrate it roughly. You start off with some parameters. With some parameters for your value function approximator. And try and so let's say we start off with that. We're going to start off with some. Okay, now we're going to try and do a step of policy evaluation here. So here we're going to do policy evaluation. Basically say, okay, we started off with some initial policy. We want to evaluate that policy as best as we can. We're not going to get all the way to the true value of that policy. We're just going to come up with some estimate of that policy. But now we're going to use that estimated value function, our best fit that we can to that value function, to give us a new policy. So we're going to act greedily with respect to our fitted value function. So we've got something like our curve here, or our spline, whatever it is, or our neural network, representing the value function as best we can. Now we're just going to pick actions greedily with respect to that value function. Once we've picked our new policy, we're going to evaluate that again as well as best as we can. We're going to evaluate that using an approximate policy evaluation. So this is something like the linear Monte Carlo methods we've seen, and the linear TD methods we've seen. We're just going to plug those in here, and then each step we're going to improve our policy a bit, evaluate that a little bit more, improve our policy a little bit more, evaluate our policy a little bit more, and so forth. And now we're no longer going to converge exactly like we did in the previous control class. We always had exact convergence to the optimal policy. Here we have to give up on that idea. There's no hope of exactly getting the optimal policy because our parameter representation just isn't good enough. We don't have enough parameters to represent, all 10 to the 170 states in Go, or all the possible things our robot can be doing. So instead we have to be satisfied with sort of the best fit we can make to the optimal value function. And so what we hope is that this process, this interleaving, is going to give us something close to the optimal value function. Okay, so let's look at this step in a little bit more detail. The crucial step then, the new step, is that we've basically taken the framework we had before, and now we want to just take each of these steps, each of these upwards arrows, we want to make some progress towards fitting our parameters towards the current policy. We're just going to incrementally keep updating and updating our value function as best as we can. And we're going to do that incrementally using the methods that we've already seen in the first part of this class. In particular, what we're going to do is now, instead of using the state value function, we're going to use exactly the same idea, but with the action value function. Just as we did in the control class, we need to approximate the action value function now. Function approximator, which is saying for each pair of state and actions, we're going to estimate some value function based on our parameters. So this is like our curve or our spline or our neural network, whatever. We're going to try and approximate the true action value function. And we're going to do that by minimizing the mean squared error between the action value function and the true action value function, which is just exactly the analogous expression to what we had before. And just the same as before, we can do something like, we can do stochastic gradient descent. And so here we have exactly the same updates as we had before for stochastic gradient descent, but we've replaced V with Q, essentially. This is just exactly the same machinery with Q. So moving the parameters now a little bit in the direction of the error in our Q values, the error we've made for a particular state action pair, with credit assigned by the gradient of that function approximation in Q. And so same machinery just applied to Q. And again, we can do this, the simplest instantiation of this perhaps is where we have a linear action value function approximation now. So we need to change the nature of what we mean by features now. Before we just have features of states. So here we're going to have features of states and actions. So this might be something now where we're saying not just how good is it, so in our robots example we have the landmark, how far am I from a landmark? Well, now it's going to be something like, how far am I from a landmark and how fast am I going? Multiplied by together. That might be a feature. How fast am I approaching it? And how far away am I from it? For each of the different landmarks. And so we're picking out features of both the state and action space. We're picking out features capturing the essence of what's important in the state space and what's important in the action space jointly. We're going to represent the action value function by a linear combination of those features, just as before. So again, we're taking the dot product of our feature vector with parameters, which we can think of as just summing over those features multiplied by some parameter saying how good it is to have that particular feature present, or big value in that feature. And we've got, again, our stochastic gradient descent update becomes very straightforward because the gradient of this function approximator is just the feature vector. And so we just update our parameters in proportion to the error and the feature vector. Okay. But just like a prediction case, we don't have QPy. We don't know the true QPy. It's not supervised learning. So we need to substitute in a target. And so again, we can have the analogous choices here, where we could do Monte Carlo, where the target would be just the return. We just plug in the return VT as the target. So this is our substitute for QPy. So now we're looking at the error between what we predicted the value would be and what the return actually was. We could do the same thing using TD0, plugging in the TD target. This is a revised estimate of how good the value is after we've taken one step. Or, again, we can, there's an extra lambda here, but using the forward view TD lambda, we can plug in the lambda return. This Q lambda just indicates that we're truncating each of our n steps with a Q value rather than a V value at the end of it, which again we had in the control class. And for the backward view of TD lambda, we have exactly the same machinery, but with Qs instead of Vs. And what we see here is we've got our eligibility being increased by features of both the state and action at each step. Other than that, it's the identical machinery. So we're just doing the same machinery applied to the action value function instead of the state value function. We've got the same choices, Monte Carlo, TD0, and the spectrum in between represented by lambda. Okay, so here's an example. This is probably the most used or perhaps overused example in reinforcement learning, which is the mountain car. And probably if you pick up, like randomly sample any paper on reinforcement learning, there's probably a 50% chance that it will have like a mountain car in it. And the idea of the mountain car is you've got some car and its state is represented by its one-dimensional position on this curve and its velocity. So again, it's just one-dimensional, how fast it's going. And the idea is that this car doesn't have enough thrust to directly get out of this big valley. So it sort of has to rock itself backwards and forwards to build up enough speed to be able to get out of this steep basin. So it maybe starts off, has to do this, and eventually shoots itself out. And the actions are basically, it can just sort of apply a thrust, a small thrust either forwards or backwards at each time step. So it's a discrete action space. It just gets to move forwards or backwards. And what happens is that we can start to plot the value function for this problem. And you see this interesting structure start to emerge. So what we're doing here, so this is actually applying the linear Sarsa control algorithm that we just looked at. So this is basically, I think, Sarsa 0 being applied to the mountain car problem. So using these TD errors and updating this value function at each step. So here we're just looking at the state value function. We can also plot the action value function. Here we're just looking at V. This is V theta. And what we've used here is this coarse code, basically. So there's a very large number of coarse pieces of coarse codes. There's basically these sort of square-shaped features representing lots of different squares across this whole state space. But there's many of them in lots of overlapping positions. So each of them generalize a little bit, but together they represent this value function with quite a good resolution. And what we see is that after, say, 100 steps of running this algorithm, so this is just running backwards and forwards for 100 steps, this shape starts to emerge. And it starts to emerge quickly because we're generalizing, even though there's a very large state space, from just 100 episodes. It's managed to just sort of generalize and get the shape of this, even though it won't have visited all of these parts of this state and action space. It won't have considered all possible velocities and all possible positions by this time. It's able to estimate the shape just from visiting some smaller proportion of those positions and velocities. After 400 steps it looks like this. After 1,000 steps you start to get this sort of spiral structure emerging here. So eventually you get this very nice spiral structure. I also have a plot for a different representation of the value function. So this is now a nonlinear, sorry, actually this is still linear Sarsa, but using some nonlinear basis function. So it's still linear Sarsa, but instead of having these sort of coarse codes that are just squares, now we have things which are basically Gaussians. So we have Gaussian features, each of which says, how close am I to some central point. And there's a whole load of Gaussians that have been thrown around representing different combinations of position and velocity, and the value function is estimated by a linear combination of all of these Gaussian response functions with corresponding parameters. And again, you can start to see, not super well on this projection mode, but you get that sort of spiral structure emerging very smoothly after a relatively small number of episodes.
David, is the goal to be just to be at that position, or be at the goal with velocity 0 or something like that?
So, yeah, there's a couple of variants. So, I think the main variant you just have to get out, and you get your there's sort of a -1 per step until you get out, and that's the problem. Okay. So this is just looking at, we've looked a little bit at lambda, and so in the lambda class we asked this question, well, is it worth bootstrapping? And so this is sort of a selection of plots for a variety of different problems. Don't worry about the difference between the different traces, this is just variance on what kind of eligibility trace you use. But what's important is that you typically get this same kind of curve recurring again and again, where lambda equals 0 corresponds to straight TD0, lambda equals 1 corresponds to straight Monte Carlo, and in many, many problems that people have tried, you get the same structure emerging, which shows that it is worth bootstrapping, but you tend to get much worse performance as you approach Monte Carlo. You do better by bootstrapping the TD0, but just as in the table lookup case, there's typically some sweet spot in between, whereby sort of averaging over all the different timescales over which you could consider these updates, you can do considerably better than either infinite look ahead or one step look ahead. So not so true for the public world, although it's still clear that bootstrapping is better than Monte Carlo. It's less clear that there's a sweet spot in Lambda that's better than zero. But for the other examples, it's true. And for many, this is an old plot. It's true for many other problems subsequently. Okay, so it's desirable to bootstrap, but does it work? So we had this issue earlier. Is this a sound algorithm? We just substituted in something into our stochastic gradient. So does it actually work? Is it a sound algorithm? And in particular, when we bootstrap, we know that with Monte Carlo it's sound because that's just straight supervised learning. It's just linear regression, and so that must converge. We want to know what happens if we use bootstrapping and combine that with linear value function approximation. And in particular, what happens if we start to mix that with other ways to generate the distribution, like if we're learning off policy, like we saw in the last lecture. So we'd like something which just works in all cases, which works, whether or not you're off policy, whether or not you're bootstrapping, whether or not you're using linear value function approximation. But there's this sort of famous counterexample that shows that unfortunately that's not always the case. I'm not going to go into the details except to say there's a very, very simple function approximator here, a very simple 6-state MDP, such that if you use this very simple value function approximator, you get this wild oscillation when you use something like TD learning or any bootstrapping method, including dynamic programming. So if you use approximate dynamic programming, you get the same problem where the parameters, instead of converging on something, just get wilder and wilder. I mean, this is a logarithmic scale, so these parameters are really going crazy. So it's a little bit unfortunate. So we have to sort of summarize where we're up to so far by saying that, if we're working on policy, now this is like Monte Carlo, TD0, TD lambda, everything works fine in the table lookup case. Everything just converged to the true value function. When we use linear function approximation, everything is still fine when we bootstrap, unless we go off policy. And if we go off policy and we bootstrap, then things can go wrong. That's not to say they will go wrong, but they can go wrong. And when we use non-linear value function approximation, if we're not using Monte Carlo learning, things can go wrong. So this sort of plot sort of summarizes it, in that we have like these three different things, and if you bootstrap and you go off policy and you use linear function approximation, then it's the intersection of these that causes the problem. So everything works just as you might hope, except when you combine all these together. So you do off policy, TD learning, linear function approximation, and there's no guarantees that it will work. Although it may work. There's also, this isn't to say it will diverge, but there's no, it's not quite ideal. And I just wanted to give a little update on this, which is based on some recent work that we did, which basically